Hello everyone. In this lecture we want to talk about intersection of lines in three-dimensional space. Why 3D and not 2D? Because in junior grades you learned about intersection of two lines in a plane. That was when you used to construct a system of linear equations with two unknowns, and we used to solve the system of equations by substitution elimination methods, and we would find the point of intersection if the two lines would intersect. That was two-dimensional. But right now, at grade 12 level, we are discussing intersection of lines in 3D. So first of all, in 2D, if I have a plane, let's say this textbook is like a plane right now, okay? It is a plane, and it's two-dimensional. What is the relationship between two lines in a plane? Either these two lines are intersecting, like I show it to you here. Okay, you see that? These two lines are lying on a plane, and they are 2D, and they're intersecting. They have one point of intersection. This is one possibility. The other possibility is that the two lines are like this. They are parallel and distinct. They do not intersect one another. Point of intersection does not even exist. Okay, so that's case 2. Case 3 is when this line is exactly on top of the other line. So you don't see two lines, you actually see one line. We call them coincident lines. They are still parallel, but they're not distinct. So 3 situations can happen in these cases where the two lines lie on one plane. I showed them to you. Now, in space of this room, if I just take this textbook away, we still have the same scenarios. Like still you can have two intersecting lines. You can have two parallel and distinct lines, okay? And you can have two coincident lines as well. So nothing is different, okay? Same 3 cases do exist in space as well. But there is one case that we do have in 3D space that we never ever had in 2D. And that is this case. So they are intersecting, right? They're intersecting like this, okay? All right, they're intersecting. Now watch what I'm doing here. I'm moving this line, farther. So see, it seems that they're intersecting, but in fact, they are not intersecting. See that? You see? So this situation doesn't exist in plane, but it does exist in three-dimensional space. So it means that the two lines are skew lines. That's what we call them. Skew lines are these lines that are not parallel and distinct. They don't have the same direction vector. They're not coincident, definitely. They're not intersecting. See, there is a space in between. There's a distance between the two skew lines, actually. And so this third case, or actually fourth case scenario, which doesn't exist in 2D, does exist in 3D space. And we call them skew lines. So that's what it is when people are talking about skew lines. That's what they're talking about. All right. So 3 cases in 2D, 4 cases in 3D. Now we have 2 points A and B in space, and there is a line passing through these 2 points. Let's say this is point A, this is point B, and we have another line that passes through 2 other points, C and D, like this one. All right, C and D. Now we want to know if these 2 lines are intersecting one another or they're not. That's what we want to find out. Or maybe these 2 lines are actually parallel and distinct. Or who knows, maybe they are coincident. And maybe they are skew lines. We don't know. We want to figure out. Okay, that's the whole purpose here. All right, so the first thing we do without hesitation is to find the direction vectors of these lines, obviously. So I'm going to find direction vector AB, which is x of b minus x of a, y of b minus y of a, z of b minus z of a. You know the formulas from the past chapters, okay? Then vector AB would be 4 minus 1, 8 minus 2, negative 3 minus 3. So that would give us 3 and 6 and negative 6. So this is the direction vector of line AB in space. Same thing for CD, okay? So I don't write the formula. It would be, okay, x of d minus x of c, y of d minus y of c, z of d minus z of c. So that would be, 0 minus 3, 2 minus 5, negative 3 minus 3. It would be negative 3, negative 3, and negative 6, okay? So we see that these two vectors are not multiples of one another. So I can tell you that AB, vector AB, is not a multiple of vector CD, okay? Because if you multiply 3 by negative 1, you get negative 3. But if you multiply 6 by negative 1, you don't get negative 3. So these vectors are never collinear. Therefore, the two lines cannot be parallel and distinct and cannot be coincident lines. So out of 4 scenarios, I omitted 2 of them right on spot right there. So these two lines, either they are intersecting lines, they have one unique point of intersection in the space, or they must be skew lines then. And that's what I want to find out. You see how I'm narrowing down my search. Okay, so for this purpose, I'm going to write the parametric equations of each one of these lines. So I'm going to go x equals, so this is for AB, and then for CD. We are writing the parametric equations. For x, I'm going to use 1, 2, 3 for the first one, and the direction vector was 3, 6, negative 6, 3, 6, negative 6. So I'll put t there, and t is a real number. So that's the parametric equation written very fast right there. Parametric equation of line CD, I'm going to use point C. Coordinates are 3, 5, 3. So 3, 5, 3. And the direction vector was negative 3, negative 3, negative 6, right? So I go negative 3, negative 3, negative 6. I will not use letter T because I have no reason to believe that these two different lines must have exactly the same parameter. So I'm going to use another letter. I'm going to choose S. And S is just like T, and it is a real number. Okay? So these two lines, if they intersect one another at a unique point, that so-called unique point must have exactly one x coordinate, and it has to have one y coordinate, one z coordinate. It can't have 10 different x coordinates. So this means that the x's must be the same. So the x from the first line should be the same as the x from the other line. 2 plus 6t should equal to 5 minus 3s, and 3 minus 6t should equal to 3 minus 6s, apparently. Okay, that's what we are thinking. Okay, so we have 3 equations and we have 2 unknowns, t and s. So we'll try to simplify these equations and solve this system of equations actually. So I get 3t plus 3s equals 2. I get 6t plus 3s equals negative 3, positive 3. 5 minus 2 is 3. And I get 6t minus 6s equals just 0. Okay, so I got 3 equations. Well, I'm going to take the first and second equations. I can number them. This is equation 1, equation 2, equation 3. I take the first 2 equations and I'm going to solve it just like I used to solve them in grade 10. So we can use elimination, substitution, any method you feel like it. Okay, so I'm going to multiply the top equation by 2, and then I'm going to subtract the equations. So I get 60 minus 60 is just 0, and that will be 6s minus 3s, which would be 3s, and that will be 4 minus 3, which would be 1. Okay, we're doing advanced math here. I'm not going to show you those basic steps that we used to do like 3 years ago. So from here, s equals 1 over 3. We found s, substitute back to find t. So we say 3t plus 3 times 1/3, we just found, equals 2. So 3t equals 2 minus 1. That means t is equal to 1/3. It was just a coincidence that we got both t and s values the same. Not always they are the same. Now, these values we're going to plug in the next equation, and we're going to sub into the third equation to check to see if they satisfy the third equation or not, and if left side equals right side or not. So we're going to plug in here. We're going to say sub into equation 3, 6 times 1/3 minus 6 times 1/3, sure enough, is 0. So that means left side equals right side. And the values of t and s we found, they satisfy the third equation. So what does that mean? It means that these two lines actually do have a unique point of intersection. That's the meaning of it. And how can we find the coordinates of that point of intersection? Well, we can plug in s equals 1/3 in the second parametric equation, or we can plug in t equals 1/3 in the first parametric equation. It doesn't matter because you're going to get the same answer. So I'm going to plug in the first one. So I say x equals 1 plus 3 times 1/3, y equals 2 plus 6 times 1/3, and z equals 3 times 3 minus 6 times 1/3. So that would be 2, this would be 4, and this would be 1. So that means that the point of intersection is 2, 4, 1. Okay, so the point of intersection, POI, is going to be not point A, but I'm going to call it point P. Okay, that will be 2, 4, 1. And that is the point of intersection. So the two lines in space that are passing through the points AB and CD, these two lines are intersecting one another at a unique point of intersection whose coordinates are 2, 4, 1. Period. Done. Next exercise, we have two lines again in 3D, and we want to see what is the situation here again. So I'm going to find the direction vector of the first line, 1, -1, 1. It's very easy because the vector equations are given. For the second line, 2, 3, -1. And it's needless to say that D1 is not parallel to D2. These are not collinear vectors. And it's very clear that D1 is not a multiple of D2. So for sure, these lines are not parallel, right? So not parallel lines. So they're not parallel and distinct. They're not coincident either. That leaves us with two scenarios again out of 4 scenarios. So these two lines could be intersecting like this situation I showed before, or maybe there are skew lines we don't know. We have to figure out. So once again, I'm going to write line 1, line 2, L1, L2. I'm going to write their parametric equations. So 2 plus t, 1 minus t, and 0 plus 1t is just t. And for the second one, line L2, it would be 3 plus 2s and 0 plus 3s and -1 minus 1s, and s is a real number. Once again, if they are intersecting, they must have the same x, y, z, which means that the point of intersection must have the same x, y, z. So I'm going to say 2 plus t should equal to 3 plus 2s. 1 minus t should be 3s, and t should be -1 minus s. So these 3 equations simultaneously must be satisfied. with unique values of T and S. Okay, so if I add the two equations up, equation 2 and 3, okay, add them up, so we get 1 equals 2s minus 1. From here, s would become 1. So s is equal to 1, we get. And when we plug in 1 in the other equation, did we do this right? We added these two equations as 2s minus 1, and this is just 1, because negative t and t cancel each other. So that gives you 2 equals 2s, s equals 1, mental math. Plug in equation, let's say equation 2, so 1 minus t equals 3 times 1, so that's 3 minus 1 equals negative t, which means that t would be negative 2. Okay, so we got t equals negative 2, s equals 1. So now we have to grab these and substitute in the first equation that we never used. Okay, so sub into equation 1, so 2 plus t equals 3 plus 2 times s, which is 1. So the left side becomes 0, the right side is 5. And anybody in the universe knows that 0 is not equal to 5. So this time we noticed that left side was not equal to right side. And the message here is that these two lines that were never parallel and distinct, that were never coincident, now we understand that they were never intersecting. And out of 4 cases, 3 is gone. So they must be skew lines, period. So we're going to say the lines L1 and L2 are skew lines, okay? And if they are skew lines, we know that they don't intersect. So there is no point of intersection for us to find. Mind you, we should be able to find the distance between two skew lines. If you have two skew lines like this, okay, you should be able to find the distance between them. And that's a whole different story. Of course, we need to follow particular procedures to do that. Thank you for your attention.